Because waves travel and move in time and in space, there is a certain amount of energy that is transported by those waves. And we can use the ideas that we took from last chapter on oscillations into the idea of simple harmonic motion. And we might think about it in this way. If I had a spring, and I have a mass, and I permit this mass to vibrate up and down, and while it's vibrating up and down, I were to allow it to move in space, then it would have the same kind of effect as a traveling wave. Now, we would want to make sure that our forces are orthogonal, which means that we don't want this oscillator to be swinging back and forth and changing its angle from vertical. We don't want that to happen. But if we can maintain this vertical up and down motion while we move it in the horizontal direction, that's what we would actually want to try to do. So let's look at how we can derive the formula for energy. But before we do that, let's take and look at some definitions. So you notice that here you have this S value. The S refers to the cross-sectional area. That the wave is traveling through. And the reason why we use S instead of A for area is because A is used for the amplitude. This is not area. So make sure you have that in your mind as to what S and A are. Make sure that's clear. And there's also rho, which everybody remembers. We call that density of the medium. And the medium, we just mean what's the wave traveling through? What type of substance? So let's start with a property of oscillating motion, and let's start with frequency. Frequency is equal to 1 over 2 pi, and in the case of a spring we have the square root of k over m. And what we want to look for or solve for is k at this moment. So I'm going to have frequency squared is equal to 1 over 4 pi squared k divided by m, and moving everything across, basically if I move this bottom part over, I can get k. We remember that the energy due to oscillating motion for a spring, we had E equals 1/2 k of the spring times the amplitude squared. Now we can put in this k value. So I'm going to have 1/2 times 4 pi squared times the mass times the frequency squared times the amplitude squared. And I can simplify with the 1/2. And now I need to look at how I can simplify this even further. Well, I know that mass is equal to something. And you think about density. Density is mass per volume. And if I think about the volume, I can get mass. So let's do mass times volume. And mass times volume is just, density times volume is just density times my surface area, cross-sectional surface area, times the distance or the length for that box. But the length, if we go back to this picture, notice that the length is just equal to the velocity times the time, the amount of time that it takes to get through that length, and we know the velocity of the wave. So we can substitute that in, so we get density times cross-sectional area times velocity times time. And now we can substitute this in for the mass. Equals 2 pi squared. Put in our value, density times the cross-sectional area times velocity times time times the frequency squared times the amplitude squared. So this is the amount of energy that's being transmitted or transported with a wave. If I want to find the average power, that's just energy divided by time, and I have the time here that I can take out. So the power is 2 pi squared density times cross-sectional area times the velocity times frequency squared times amplitude squared. And another parameter, average intensity. So I'm going to put this out here. Average intensity and let's put this definition here. This is average power. Okay, so the intensity, I, is equal to the average power divided by this cross-sectional surface area, and that's equal to 2 pi squared density times velocity times frequency squared times amplitude squared. This is the amount of intensity that we have through a specific surface area. Now we're going to use these formulas to calculate different properties, and it's especially important when we talk about isotropic mediums and the point sources. We'll be able to understand how these formulas work. But for right now, just understand or have in mind what these formulas represent, and then we'll talk about how to use them in the next few lectures.